So, hi everyone, welcome to the 7th talk of the SPML seminar. I believe this is the third back-to-back talk we are having on privacy mechanism. So that's great, this continued discussion. Our guest speakers, as you know, are Soham and Leonard Berrada. Hopefully I didn't butcher the name, from Deepmind. They'll discuss how we can train very effective classifiers using very effective differentially private classifiers using scales and many other techniques they have developed. To give a brief background, Soham is a senior research scientist at Deepmind. He received his PhD from University of Maryland. Leonard is also a research scientist at Deepmind. He received his PhD from University of Oxford. Sorry, I should have said Soham is actually a senior research scientist. So yeah, congrats on the promotion. Sorry, I didn't mention it. Again, a bit on logistics and to our speaker. Generally, the talks we schedule around 40 minutes for the talk and 20 minutes for the discussion. So we appreciate if you leave some time for them. And to the audience, please ask a lot of questions. Either way, post it in the chat or ask the speakers directly. But let's keep it. Let's give our speakers a bit hard time. So with that note, the virtual stage is all yours. Please.
Great. And yeah, feel free to ask questions during the talk. Okay, so thanks very much for having us. We are very happy to be presenting this work today. So this is this paper, Unlocking High Accuracy Differentially Private Image Classification Through Scale. So I'm Leo and this is Soham, and we are presenting this work that we've done with other collaborators at Deepmind, namely Jamie, Sam, and Borja. So our paper is available on GitHub at this link here, and the code is available on GitHub as well. So why do we care about training machine learning systems with differential privacy? Well, it's because machine learning models can leak training data, and this very commonly used XKCD very explicitly show this. How when we train models based on sensitive data and we deploy the model, then this model might leak some sensitive information. So this has been shown in the literature on language models, for instance, through this work by Carlini et al., where they show that from GPT-2 that has been trained on web data, they're able to extract sensitive information. But also, perhaps more surprisingly, even from image classifiers, it's possible to successfully reconstruct training data points just by looking at the model and having some knowledge of how the model was trained. And this is work by Borja, Jamie, and the collaborator that has been published recently. So based on this observation that machine learning can leak training data, what we want to do is to train models with differential privacy while keeping high accuracy as much as possible. And that's what we're going to talk about in this work. So if we look at the state of the art when training models with differential privacy, so on the left, this is the SOTA on CIFAR10 over time, where we can see that the progress has not been so fast and that the accuracy until the beginning of the year was still under 72%. And on the right-hand side, we can see that the accuracy of a model trained with differential privacy on Imagenet has very poor performance compared to the state of the art, when there is the state of the art of like without differential privacy. And so the main results of this work is that we are able to significantly improve upon the prior work. And so on CIFAR10, we are able to get the largest improvement to date. And on Imagenet, we're able to significantly bridge the gap between non-private and private performance and reach levels of accuracy that allow us to start to talk about practically useful levels of performance. So how do we get these results? This is what we are going to be discussing now. And the outline of the talk is as follows. So first, I'm going to talk a little bit about the background on differential privacy and differentially private stochastic gradient descent, or DP-SGD in short. Then I will talk about the main aspects that we have detailed in a paper that help improve convergence and trainability of deep neural networks. And then Soham will talk about leveraging pre-training and give some intuitions about the interplay between noise, batch size, and compute budget, which are all very important hyperparameters in practice. So let's get started on the background section. So without getting into too many details and the math of it, at a high level, the guarantee that differential privacy gives us is or like one property that is essential about differential privacy can be described as follows. So if we have in yellow an epsilon, so a differentially private algorithm that is randomized and that gives a differential privacy guarantee of epsilon, then if we train one data set with this algorithm and this data set includes my data, then this induces a distribution over models that we call P here. And if we use the same algorithm to train on the same data set, except that it does not include my data, then it induces another distribution over models that we call Q. Then one key property that differential privacy gives us is that the distance between the two distributions is bounded by epsilon squared. So if we look at the KL divergence. So intuitively, if epsilon is small, then the two distributions are very small. And so we cannot tell just by looking at these models whether my data has been used for training. And this is the guarantee that my data is protected. So beyond this mathematical property, differential privacy is very desirable for deploying models on sensitive data. This has been used in a number of applications, both in government, like in the US Census, and in industry, in all these companies like Meta, Microsoft, and so on that you see here. And some of the desirable properties are that one, it's robust to powerful adversaries, and that includes adversaries with unbounded computation and that have arbitrary sign knowledge. The second point is that it does not rely on obscurities, and we can release publicly the algorithms that we use for training. And then finally, we can quantify the level of privacy that we can guarantee with this parameter epsilon. Now, this privacy budget epsilon is really a policy question that should be informed by the normative requirements for each application. And that depends also on the utility versus accuracy requirements for each application. So we have plotted here a few values of epsilon that are used in practice. And in this paper, we mainly look at epsilon between roughly 1 and 8, with 8 being standard for comparing against a bunch of state-of-the-art results. And yeah, one thing that is important to note and to keep in mind is that there is more privacy when epsilon is small and less privacy when epsilon is large. So how do we train in practice a model with differential privacy? So we are just modifying the updates that is performed at every step. And in spirit, it's really similar to stochastic gradient descent, except that we privatized the gradient. So the setting is that we are considering a trusted party that trains the machine learning model on a private data set. And on each update, we're only going to use, we're going to privatize this gradient so that we can bound and hide the influence of any single data point. And because every single update that we use during training is privatized, then the model can be released at any point during training, which is a property that we will use in a bit later in the talk. So how does this privatized gradient look in practice? Well, it's really similar again to a standard gradient with the exception of two main modifications. The first one is that each gradient per sample is clipped to a maximum L2 norm of C. That's the blue term here. And on top of that, we are adding some Gaussian noise that is proportional to C, the clipping norm, divided by the batch size, and sigma, the noise hyperparameter. So it's when we look at this equation, it's and this update is obviously repeated at each iteration during training. So it's worth also keeping in mind that the privacy loss epsilon will increase with the number of iterations. So with the number of times that we're going to be applying this update, it will decrease with the added noise, because the more noise we add, the better we protect the privacy of our data. And it will increase with the batch size, because each update will have seen more data points. So if we take this update and we plug into a machine learning pipeline to train a standard model, this will create a number of challenges. The first one is that usually we are given a privacy budget epsilon, and this creates a trade-off between the number of iterations and the amount of noise that we're injecting, so that they fit the privacy budget that we are given. And so we cannot, for instance, hope to run our training forever so that the noise that we're injecting just washes out with the whole iterations, because that would not respect our privacy constraint of not spending more than epsilon privacy. And then because of that, because of that and because of the noise that we're adding, in practice, the hyperparameters that people are using as default values and the regularization schemes that people are using can be completely unadapted to this setting. And so we have to really be careful about how we choose to tune our hyperparameters and how we choose to regularize our model. The second challenge of DP-SGD, if we zoom into that equation, then from an optimization perspective, the privatized gradient that we're using is biased, because the clipping per sample reweights the importance of the different samples in the average. And the second one, which is even more important, is that this privatized gradient has high variance, and that's because of all the noise that we're adding. And in our experience, this is really the bottleneck to getting good performance, is fighting against this noise that is being added. And lastly, the last challenge of using DP-SGD in practice is that it does not necessarily work completely out of the box with standard models. One reason is that the typical computer vision architectures employ models with very large number of parameters. And so the norm that we're adding is in very high dimension. And so this the importance of this noise can be overwhelming in high dimension. And the second aspect is that a lot of computer vision architecture use batch normalization as standard, and batch normalization cannot be very easily adapted to fit the differentially private updates. So the approach that we suggest in this work is first that we are going to use standard deep learning architectures instead of focusing, like some prior work, on customizing the choice of activations or architectures, because we think that using these standard deep learning architectures have been really designed to have large expressivity and to scale to large data sets. So we think that this is the most promising way to actually scale DP-SGD to very challenging tasks. Second, we're going to push the limits of vanilla DP-SGD without making fundamental changes to the algorithm. But we're going to use enough compute and tune the hyperparameters of the method carefully so that we can really push the performance of DP-SGD as much as possible. And finally, we're going to reuse some tricks that have been shown to help for non-private training and adapt them to improve the trainability and convergence of DP-SGD in practice. And it's worth emphasizing that getting all of these details right was really crucial to get good performance. So I'm now going to talk about how to improve convergence and trainability of deep neural networks in practice when we train with DP-SGD. So what I'm going to show next is an ablation study to understand which components matter for good performance when training with DP-SGD. So the setup that we are going to be looking at is as follows. So we're going to look at CIFAR-10 classification with the differential privacy parameters of epsilon 8 and delta 10 to the minus 5. And we're going to be training a Wide-ResNet, which is a variant of convolutional neural network with depth 40 and width 4. It will be denoted by WRN44. And the approach that we're going to have is to add a single ingredient at a time to show the effect that it has on performance. So the baseline model that we use is this Wide-ResNet 44, from which we have that usually uses batch normalization, but we have removed it because batch normalization introduces dependency between the different samples at training time, which does not play well with DP-SGD. So we just remove batch normalization, and then we train our model with DP-SGD. And when fine-tuning the hyperparameters, we get around 51% accuracy. And so on the bottom right here, what you see is a depiction of the skip connection in each block, which has batch normalization, then ReLU, then convolutional layer. So the first thing that we do is that we replace where there used to be a batch normalization layer, we put a group normalization layer, which is another way of normalizing the signal. And that we're really here exploiting previous work in in non-private training, where people have shown that we can recover the benefits of batch normalization by either using other normalization methods like group normalization, or so-called normalizer-free methods, where we're just rescaling the signal through a scaler. And so whether we are using another kind of normalization or a scaler, we denote this method by alpha, and we emphasize here that it's really crucial to place it on the residual branch to really recover the benefits of batch normalization by improving the signal propagation through the network. And so, yes.
So sorry to interrupt. The group knob is only placed on the skip connection, or like everywhere?
So it's placed on the residual branch, so not on the skip connection.
Oh, sorry. Oh, it's on the residual, not on the skip.
Yeah. Right. So it's where alpha is right here.
Okay.
So, and just by this simple change, we observe this massive boost of performance to reach 66% validation accuracy. Now, the next trick that we use to improve convergence is to increase the batch size. And this is an observation that is consistent with other work on training with differential privacy, where basically we see that using a large batch size really helps improve the signal-to-noise ratio of the privatized gradients. And so on the bottom right, each of the points for each of the batch size values, we are tuning the hyperparameters of a model with using the batch size specified on the x-axis. And then on the y-axis, we plot the training accuracy and the validation accuracy. And we see that we get pretty much consistent improvements as we increase the batch size. So using this batch size of 4096 gets us to 70% validation accuracy. We also, another way to improve the signal propagation is using this method called weight standardization, which I'm not going to detail here, but just renormalizing the parameters of the model as part of the forward pass, which also gives 1% improvements. And then another method that was really helpful to improve performance was to use augmentation multiplicity. So what augmentation multiplicity is it's a kind of data augmentation. So the most common way of doing data augmentation in, let's say, image classification is that when you have an image that is given to your classifier, so let's say here the image of a fox, then you might do a random horizontal flip. So the left image out of the block of 3 here, or we might take a random crop. But usually this augmentation is used on its own. So each element of the mini batch is randomly modified following this augmentation methodology. And then these modified images are fed to the model. And some people have observed that what you can do instead of just using one augmentation per sample within your mini batch is that you can use several augmentations at a time. So here, for instance, if you use 3 augmentations, your batch size would increase 3-fold. And this has been shown to improve performance in a non-private training, but it's especially useful in private training because we can combine this information, and these different augmented data contributes to a single unit of privacy. In a sense, they all come from the same data, so we don't pay an extra cost from looking at different augmentations of the same image. And because of that, we are able to use updates that are combining the information from these different augmented images without paying any privacy cost. And so really what this augmentation multiplicity does is that we're benefiting from data augmentation and from the reduction of variance that it brings, but without paying any privacy cost. So when we look at this bottom right plot here, when we're plotting the accuracy as a function of the augmentation multiplicity, so the number of times that each sample is augmented within the mini batch, then we can see how we're getting really consistent improvements on the training and validation accuracies by just using a larger amount of augmentation multiplicity.
Can you clarify the equation on the last slide a bit more?
This one?
So you like, is it are we adding the noise? So we are adding the noise after we kind of like average the gradients from different augmentations, right?
Yes.
So I'm a bit confused like about the variance part, because it's not, this is not the same effect as increasing batch size, because there we do reduce the variance,
right?
The stochasticity due to noise.
Yeah, this is the variance that comes from the data set itself, not the Gaussian noise that we're adding.
I see.
So we're by combining these different augmentations, we are getting more information, and therefore the average gradient over the different augmentation will be a bit more representative of the rest of the data sets.
I see.
So you're reducing like the gradient variance, even like without thinking about the Gaussian noise.
Okay, so got it. So more from.
Just to add on that, like, if you consider, for example, the random crop function, like that has some randomness in it. Yeah. Like there's a bias and a variance of that function. And when you like average over different random crops, you are like averaging out kind of the variance part of that function. So that's what we kind of mean by averaging out the noise or reducing the variance.
I see. So it's hopefully converging to like the actual gradient of x naught. Like.
Yeah. So I mean, ideally, you would have, like, if you had infinite computations, then you would do like all possible augmentations in the world and like combining the gradients for them together. And that would give you, in a sense, the sort of the base gradient that you can get out of this single image. And here we're just like increasing and you can look at a single gradient, like based on a single augmentation as just like an estimator that has high variance of this, like ideal gradient that combines all the augmentations.
Yeah, precisely. So I think the follow-up question is, one thing is like we can not apply augmentation, because then in that case, we do get, like if we consider X naught as the image, so here we have transformed X naught, and then we reduce the variance by using K different augmentations. Mm-hmm. So it's like if you just not apply any augmentation at all, just consider the gradient of X naught, versus if we consider the augmentation multiplicity. So it kind of feels like the gradient we get, this like averaged out gradient we get from different augmentations, not only reduces the variance, but somehow this is more like the better direction for the model to move in, even when we have this stochasticity.
Yeah, exactly. Like the augmentation function has a bias. So like when you average over the augmentations, you're sort of converging towards that like ideal augmented image, basically, instead of the original image, which is, I think, what you're referring to as X naught.
I see. So, okay, got it. So it's not like, maybe it's not the gradient of X naught wasn't maybe the best direction to move in. So, okay, so got it. So it's maybe like over the augmentations, you figure out the best one. Thank you.
Yeah. Are there any other questions?
May I ask a question?
Yeah.
Yeah, I did not fully understand the privacy cost of this data augmentation step, because when you do data augmentation, you essentially repeat someone's data in different views in the data set. Okay, so which to me decreases the privacy guarantee for that individual, because multiple versions of that individual data is present now in the database. So even with the same epsilon value, the privacy guarantee for that individual has been reduced. So how do you justify this?
Yeah, so the idea is that the way we're privatizing the update is through this like sort of Gaussian mechanism, where like basically you bound like the influence of any particular sample on your updates, and you add noise on top of it to mask out any individual contributions. But what is inside this thing that you're bounding, like as long as it depends on one sample, it does not matter much what you're like how it's been computed. So you can compute like the gradient based on the one image, or it can be the average over gradients computed on several augmented views of the same image. But because it's done before the clipping and the noise addition, then it's really the same privacy cost.
I see, but when calculating the sensitivity, we say that the sensitivity is calculated by adding or removing one individual from the data. Yeah. So now in this case that we have multiple versions of someone's data in the data set, so how does this change the privacy cost? If we want to remove that individual, we have to remove all the augmented versions of that one's data.
Yes. So if we like the sensitivity of like this update that is displayed at the bottom here is like the L2 sensitivity is going to be 2C over B and over the batch size, and you can see that it matches, right? Like if we remove one of the samples, then and this like sensitivity of 2C over B is like the multiplying factor for the noise, just so that it matches. And so you can see that if we remove one sample from our mini batch, then we remove like K, like this average over K gradients, but this average over K gradients just had an influence of C, right? Because it's the average itself that is clipped to C. So like it just checks out in this way. Like we are like still having the sensitivity that we expect here. Like what would not work is if we were clipping on the inside of the average over K. That would be a violation of the guarantee that we're trying to get.
I see, got it, thanks.
Yeah, nice. Okay, and so the last trick that we use to improve convergence and trainability here is that we're using parameter averaging. So this is really exploiting the fact that, as we've said before, we can release the model at any point during training, and so we can also compute an exponential moving average of these parameters over all the updates done so far, and use this for evaluating our model. And then this is because like this averaging of the parameters tends to reduce the oscillations during training, and so in practice it does improve convergence and improve the performance by 1 to 2% in practice.
Leonard, we do have a question in the chat, so do you mind addressing it?
Yeah, absolutely.
Thank you.
Right, so the question is, when you say larger batch size, do you mean larger micro batch size for DP-SGD? DP-SGD applies DP per micro batch, which should be a multiple of batch size. Applying a larger batch size will have no effect, I guess. It should be micro batch. So I'm not exactly sure what the question is here. It could be like, I think I remember that from TensorFlow privacy, there was this naming convention of micro batch, like you clip basically once you've taken the average over the micro batch only. But that would not be consistent with what we're doing here. So I don't, Vikash, do you have?
Or Ali, do you want to clarify the question a bit? I'm not quite sure what you mean by micro batch.
Yeah, sure. If you see the convention in TensorFlow, they mentioned that DP-SGD applies differential privacy per micro batch, not the regular batch size of our machine learning model. So which should be a multiple of the micro batch size should be a multiple of the batch size machine learning models. So when it applies the differential privacy, it's per micro batch size, not the batch size. So I'm not sure if you are using the micro batch sizes larger. So if you make the micro batch size larger, yeah, definitely the noise is reduced per more samples, so the ratio decreases. So if you just use a larger batch size, regular machine learning size, so it will virtually have no effect because it's still going to apply per micro batch size.
So does the macro batch size of 1 correspond to the rate being clipped per sample?
Yeah.
Okay, so we are always using micro batch size of 1 then.
Oh, okay. Yeah, sure. Thank you.
Yeah, no problem. Okay, and now I'll hand over to Soham.
Right, thank you, Leo. Putting all of these tricks for improving the convergence and trainability, here are our best results on CFAR10 classification, where we don't use any extra data, so training from scratch. So in this plot here, we're plotting on the y-axis test accuracy versus on the x-axis epsilon, which is the privacy budget. So an epsilon of 1 is very more private, and an epsilon of 8 is less private. And in blue, we're plotting our best results, and we're comparing in other colors with all the previous papers on this task. And as you can see, so epsilon 8 is kind of a community standard for comparing these models. And at epsilon 8, you see that we get a large improvement over prior results. It's close to a 10% improvement. And we are kind of better than prior results at all epsilons greater than or equal to 3. At epsilon 8, we get around 81.4 test accuracy. And this blue curve is with a 40-layer Wide-ResNet, and kind of we scaling up the batch size, the augmentation multiplicity, and the compute, and using all the other tricks that Leo mentioned. And it's what kind of, so this is kind of we think it's a significantly larger network with that we train with DP than previous work, and we were able to do this because we kind of were careful about the signal propagation and the convergence of the model, as Leo described. Another thing worth pointing out is that you notice that like at epsilons 1 and 2, like this paper by Trammer and Bonnet outperform us. So this is a model that uses kind of handcrafted features and then learns a linear classifier on top, which is very hard to scale to more complicated problems. And we kind of took the approach of trying to train large, highly kind of over-parameterized models because we think, as Leo said, like we think that's the easiest way to scale to more challenging tasks and data sets. We can also do Imagenet classification in the same way without extra data from training from scratch. Here, there's only, I think, one previous paper with a baseline, the Skorakan et al. Paper, which uses like an 18-layer ResNet and gets like around the top one accuracy of 7%. And we didn't tune our numbers too much, but using like a 50-layer normalizer-free ResNet at epsilon 8, we get around 32% top one accuracy, which is quite a large jump. So like this is using a 50-layer ResNet and combining it with the tricks that Leo mentioned. So this is quite a big jump, like on both CFAR and Imagenet training from scratch. But you know, like there is still quite a large accuracy gap with regular SGD training. So next, I'm going to talk about how we can leverage a large-scale public pre-training to really close the accuracy gap between private and non-private performance. Before going there, I just want to again quickly stop if there's any other questions.
To clarify, Soham, with DP-SGD, it's more of like a convergence issue so far, like even in your thoughts. Okay.
Yes.
So the more we push on that, the more likely we will benefit.
Yes, definitely. The added noise kind of increases the variance to an extent where we can't even fit the training set on CFAR 10, for example, which is very different from non-private training. And it's all about how well can you converge. And any improvements in performance on the training set directly kind of translates to improvements on the test set or the validation set.
Yeah, thanks.
All right, so how do so we kind of now we show that we can leverage kind of large-scale public pre-training combined with deep, highly over-parameterized networks to almost close the accuracy gap between private and non-private training. And so the setting we're going to use is the following. So first, we're going to pre-train non-privately, so using SGD, on some extra data. And this extra data we're going to assume is public or kind of doesn't contain any kind of sensitive information. So we can pre-train non-privately. And then the second step is to fine-tune privately on our private data set using DP-SGD. So we can consider like similar tasks of CFAR 10 and Imagenet classification. So here's our best results for CFAR 10 fine-tuning. So here we are fine-tuning privately using DP-SGD on CFAR 10. And we are pre-training, first we are pre-training on a downsampled version of Imagenet, and then pre-training non-privately, and then fine-tuning privately on CFAR 10. And so we compared like fine-tuning just the last classification layer and fine-tuning all the layers. And we found that fine-tuning all the layers for this task worked better. And so here are the best results we got. So this is with, I think, 2810 Wide-ResNet. And we see that like at epsilon 8, for example, we get around 96.6% training validation test accuracy. At epsilon 1, we get almost up to 95% test accuracy. So these are kind of numbers very close to the non-private performance you would get with this model, with these Wide-ResNet models. So we're almost closing the gap between kind of private and non-private performance. And we can extend these results to start to do fine tuning with DP-SGD privately on Imagenet. So for these experiments, we pre-train non-privately on JFT, which is this image classification data set that Google has. So this plot here, for this plot here, we pre-train on JFT 300 million, and then fine-tune privately on Imagenet. And so on this plot, we are on the x-axis, we are showing different models, going from Normalizer-Free ResNet 50 to Normalizer-Free ResNet 200. So from left to right, the model size is increasing. And we're plotting the top one accuracy across a range of these range of models, where we both fine-tune only the last layer and fine-tune all layers. And so first of all, we see that fine-tuning just the last layer in this case is better, unlike the previous task. And more interestingly, perhaps, that we see that consistently using a larger, better pre-trained model is better for fine-tuning performance. So like going from ResNet 50 to ResNet 200, we continuously improve performance on Imagenet. And these are numbers with epsilon equals 8 under a fairly small compute budget to just compare these two settings. So now we also wanted to see the effect of the pre-training data set. And so here we are comparing two pre-training data sets, a JFT 300 million, which has 300 million images, versus a data set JFT 4 billion, which contains 4 billion data sets. And we're sort of controlling for the amount of pre-training compute. So we're pre-training for the same amount of time on both data sets, but we wanted to see the effect of kind of using a larger, a better, more diverse pre-training data set. And we see that, so these are results with ResNet, Normalizer-Free ResNet 200, and kind of scaling up the batch size and compute. And we see that across a range of privacy budgets shown here on the x-axis, we see that pre-training on a better or a larger pre-training data set is always better for better downstream fine-tuning performance. And you can see that at epsilon 8, for example, our Normalizer-Free ResNet 200 gets up to like 82.2% top one accuracy. So kind of combining these insights, our best results on Imagenet came from using a better model. So we use a Normalizer-Free network, the F3 version of this Normalizer-Free network, which we pre-train on JFT 4 billion, which is the largest kind of pre-training data set we have. And combined with kind of scaling up the batch size and the amount of compute we use, these are our best results. So we are plotting the top one accuracy versus at different privacy budgets, epsilon. And we see that, at epsilon 8, for example, we get up to 86.7% top one accuracy, which is extremely high. And even at extremely tight privacy budgets like 0.5, we get top one accuracies of 83.8%. And like comparing this with the non-private SOTA on Imagenet, which is at 91, we are remarkably close. And like if you kind of take the same model, the NFNet F3, and you train it non-privately, we see only like a 2% gap between the private NFNet F3 and the non-private NFNet F3, which is which tells you that we are almost closing the accuracy gap between these two models. And just to kind of see whether our kind of main insights translate to settings where there's a slightly larger distribution gap, distribution shift, we see that we tried fine-tuning on places 365, after pre-training on JFT 300 million. And we see again that like we can almost close the accuracy gap between private and non-private performance. And on this task where there's a slightly larger distribution shift, we found that fine-tuning all the layers performed better than fine-tuning the last layer. All right, so I'm quickly going to finish off with some kind of insights on hyperparameter tuning for DP-SGD. So as kind of Leo mentioned, DP-SGD requires extremely careful hyperparameter tuning. There's lots of different hyperparameters to tune, and it's not always clear how they interact with each other. So we did some kind of simple studies to get a bit more insight into kind of simple rules of thumb that we can apply when tuning DP-SGD. So the first question we kind of asked ourselves was that, is it better to always train for as long as possible with DP-SGD while increasing the kind of noise you add? Or is there kind of an optimal time, optimal noise scale and an optimal kind of compute budget for which to train with DP-SGD? So these are plots. So this plot here shows kind of the accuracy versus models trained at different noise parameters. And so each of these points are independently tuned. And we see very clearly, so these are results at a fixed batch size. And we see that very clearly there is a peak in performance at a particular noise scale. And so like this means that there is an optimal noise scale for a fixed batch size. And we saw this property across a range of different experiments that we ran. And because a noise scale kind of determines how long you can train for, this also means that there is an optimal compute budget. So in the middle plot here, I'm plotting the same plot as the left one, but instead on the x-axis, I'm translating the noise parameter to how long we train for, the training iteration budget. And on the right plot, we're showing, instead of the validation accuracy, we're showing the training accuracy at those same training iteration budgets. And we see in both cases, we see a peak in the performance at the same point. And so this means that there is an optimal compute budget for both the training and the validation accuracies with DP-SGD. And kind of interestingly, this is quite different from non-private training, at least on the training set, where on the training set and non-private training, training for longer is almost always better, and you always reliably decrease the training set performance. And finally, like this optimal compute budget, we found that this kind of depends on the batch size in an interesting way. So on the left plot, we're plotting the optimal iteration budget for different batch sizes. So again, each of these points are independently tuned. And on the middle plot, I'm sort of showing the same plot, but like translating it to optimal epochs for different batch sizes. And we see that before a certain threshold, so before like the threshold of a batch size of 2 to the 11, on the left side of the plot here, we see that increasing the batch size doesn't require us to use more compute, so we can use a constant number of epochs as we increase the batch size up to a threshold. But after that threshold, to get kind of optimal performance back, we need to keep increasing how long we train for. So we need to keep increasing the number of epochs we train for after a certain threshold. And so like DP-SGD is really like compute efficient up to a certain batch size threshold and sort of starts becoming compute inefficient after a certain point. And this kind of point at which it starts becoming compute inefficient is the point where the optimal learning rate sort of becomes constant with the batch size. So on the right plot, I'm showing the corresponding optimal learning rates at different batch sizes for these same plots. And we see that like before 2 to the 11, the optimal learning rate scales linearly with the batch size up to that threshold, and then it sort of becomes constant. Okay, so to summarize, we showed that standard vision models can work surprisingly well with DP-SGD when we combine it with tricks to improve convergence and trainability of deep networks, and do careful hyperparameter tuning and use enough compute. And when you combine these standard vision models with kind of large-scale public pre-training, we get practical levels of performance with DP-SGD. And all our code is available at this GitHub link. And finally, I just want to end on a note of caution. Like, while we kind of mentioned practical levels of performance, there's still lots of additional open questions that we need to solve before we can sort of actually deploy models with DP-SGD. We need to think of what the right level of privacy budget is, what kind of privacy we want to guarantee in the first place. We need to do very careful evaluation to avoid kind of disparate impact on kind of outliers and so on, and the sensitivity of the pre-training data set. So there's lots of open questions to solve before we can think about really deploying these models in practice. And with that, I'll end, and thanks a lot again, and we're happy to take your questions.
We have one in the chat.
I can ask another question.
Yeah.
So my question is, if you have tried your model which you train using DP-SGD against those attempts which try to reconstruct the training data from the gradients or the shape or the parameters of the model, because at the end of the day, the model learns the data. As you see that your model has like 83% accuracy, so it means that your model has still learned the data. So have you tested your model which was trained under DP against those models to see if it really provides privacy? I know that theoretically you have some privacy budget. I mean, if you have tested your model against those attacks.
So do you mean have we tested the empirical privacy of the model?
No, I mean, have you tested? You have trained a model using differential privacy, right? So have you tested this model against those attacks which try to reconstruct the data from the gradients? Yeah, I know that theoretically you have some privacy budget. So, but as you see that as our accuracy improves, it means that our model is still learning information, right, from the data. Have you tested against those attacks?
So we haven't run reconstruction attacks from the gradients themselves, but like Jamie, who's on the call here, has run some membership inference attacks to get some lower bounds on the epsilon and check that there was not any violation. Do you want to comment, Jamie?
Yeah. So we ran membership attacks and they basically failed in that like we didn't see that there was like these membership attacks would work that successfully. I personally have also run reconstruction attacks in the set in like the flavor that you have described, where you try and attack do reconstruction against like optimizing against to like match a certain gradient, and that also fails for like reasonable epsilon. So it's like as long as your epsilon is like smaller than 10, like these attacks seem to fail.
Oh,
so yeah.
Thank you.
To follow up on that, actually, so I have like this broad overarching question. I'm pretty sure, like Soham and Leonard, like you have, like this question had come up like many times. So regarding the use of public data set, I understand like that last layer fine tuning works pretty well, but there are like certain fine tuning settings where we cannot escape the necessity of training the whole network, or something like where pre-training is good, but it doesn't land us in like sort of like in the in the parameter space. It doesn't move us close to sort of like the optimal solution for the downstream domain. One being, for example, semantic segmentation. So there might be cases where we may need to train a lot, even after pre-training. And it feels like even though pre-training and sort of like all the techniques you have developed, they give us sort of really much better performance. But fundamentally, DP training do remain hard. And it's sort of like the Imagenet experiment you showed, where if we fine tune all layers, which means the more we train the more part of the network we touched with DP, the more the performance went down. So like feels like we haven't like escaped this limitation of DP we have.
We completely agree with your statement here, and this is something that we're actually also showing in our paper. So like we maybe didn't have time to go too much into the details of these numbers here, but if you see the performance that we get on places 365 here, you can see that fine-tuning all the layers is better than fine-tuning only the classification layer. And this is, I mean, as you're saying, basically, there's basically a whole spectrum of difficulty of fine-tuning, right? Like JFT to Imagenet have low domain shifts, so we can get away with just fine-tuning the last layer. But on like harder tasks, and I was like Imagenet to CFAR, that was true also for JFT to places 365. It was significantly better to, or here maybe like a little bit better to tune all the layers. And we completely agree with this idea that when the fine-tuning task is harder, like the fine-tuning target distribution is further away from the pre-training distribution, then this all seems to correlate very well with the need of fine-tuning more of the layers.
Yeah, that's true. Regarding the use of public data set, and this is something I wanted to get your thoughts on, is more like a downstream potential downstream work. Is that the public data set can also be used like can be further integrated. So for example, like even in the DP-SGD like framework itself, one can still use the public data set. I'm not sure how, but if you make this assumption, one thing is like how realistic this assumption is in the DP domain of assuming like access to like a fraction of public images for some calibration versus assuming access to 4 billion, which has a lot, I guess has everything. Like it's a really good vision domain prior, and I'm not sure even the privacy implication of that one.
Yeah, that's a good question. I think I think pre-training on some public data is going to be kind of a fairly practical setting. Like there's going to be some reasonable practical public data set that we can access to, which we can pre-train on. But yeah, I think definitely there's work to be done on better understanding the impact of how large this needs to be, how long you need to train for, and so on. Because in many domains you won't have such a large pre-training data set.
And there's also a ton of questions about how you do this optimally, right? Like taking, like if you have a mix, like in realistic scenarios where you might have a mix of public data and fine-tune and private data, there's nothing that tells you that it's best to just like fine-tune on your public data and then only like fine-tune on the private data. Maybe you want to do a mix of both. Like I think you were suggesting, Vikesh, so like there might be ways of combining these two information also that might be more efficient than what we're doing here. I guess the sort of approach that we have here is the advantage that it's very simple, right? Like you just like pre-train and fine-tune, and it's like a simple demonstration of how effective pre-training is. That's what we're looking for.
Yeah. So we are a bit over time, but sorry, since we have you guys, let me take this opportunity to kind of like follow up on Soham's comment there, and everyone else. Yeah, please feel free to ask the questions since I guess I'm taking otherwise all the time. So in vision domain, actually, there is some work very recently, and I think one is actually from your alma mater, Leonard, if I remember correctly, about using synthetic data, like something like texture images, like completely, like there is no, there is no like real domain signal in them, and you pre-train on them and still it gives decent, if not the best performance. And that's something maybe could be extended to multiple domains.
Yeah, this is a very good point, and this is something that we have briefly discussed at some point, never got around to trying, but these synthetic data sets that don't have any data but seem to be like enabling good representation learning is a great way to like try to get the same effect as pre-training, but without any single privacy concern. So yeah, very good point, and I'd be very curious to see like if we can like how good this can be in practice.
Yeah. Let me make sure there are no questions in the chat now. So if anybody else don't have any question, let's thank our speakers. And yeah, thanks Leonard for giving such an amazing talk. So yeah, I didn't get a chance to say it earlier, but yeah, big shout out to also making the code public. Again, I have personally used that, so everyone else, like this is an like really amazing piece of code. So if you guys maybe like a noob like me in DP, or even if you're an expert, it's like super clean, super extendable code. So give it a try. And this is a very independent evaluation. There is no.
Thanks a lot. Thanks a lot for the invitation.
Yeah. Yep. So again, thanks guys, and see you everyone next week for the next seminar. Bye bye.
Thanks everyone. Goodbye.
Thank you.